Hello everybody, this is Armando Duarte from the University of Illinois at Urbana-Champaign, and today we are going to discuss GFEMgl Junior, which is a Matlab implementation of the generalized finite element method with global local enrichment functions. So start by going to the folder where you have the GFEMgl Junior source code. In my case, it's shown here at folder GFEMgl Junior, where I have the several Matlab source files and folders that we are going to discuss next. In this folder, there is a file named readme gfemgl.txt. So open that file. I have it open here on the left-hand side. And this file provides an overview of the GFEMgl Junior code and how to run it. There are several examples that we are going to look at some of them in the folder tests/598 final project 2015. It also says here the type of elements that are implemented and the type of boundary conditions that are used in the local problems. And in this case, we see that only Dirichlet boundary conditions are supported. For your Matlab setup, don't forget to add these 4 folders to your Matlab path. So here I have the Matlab screen, and I have the GFEMgl Junior.m open, and here I have the set path button. If I click it, I see that the folders GFEMgl Junior / GFEM utils, GFEM bar, GFEMgl utils, and P bar, and so on, they are added to the path according to following the instructions in the readme file. We can close this now. So moving on, it provides here now instructions on how to execute GFEMgl Junior, and when you run it, it will actually run 3 other Matlab programs. The one to solve the initial global problem, another one to solve the local problem, and finally the third one to solve the enriched global problem. We refer to these as subdrivers, and you can find details about them in their corresponding source code. We need to specify the name of the files, defining the initial global, local, and enriched global files when running GFEMgl Junior. We are going to show an example later. And after you run an example, 3 figures will be displayed. The first one, you show the solution of the initial global problem. The second one, the solution of the local problem. And finally, the third one, you show the solution of the enriched global problem. And also, it will print to the screen the energy of the initial global, the energy of the local problem, and the energy of the enriched global. These are strain energies of these problems. And after that, the code you finish, and if you look into the source code of GFEMgl Junior, you see that at the end of the file, you see the calls to the subdriver for the local problem and the subdriver for the enriched global problem. If you want to perform global local iterations, you just need to cut and paste these 2 calls repeatedly. So if you want to perform additional iterations again, you just copy these 2 calls as many times as you want to iterate. That's it for the overview. We can now move on to the next topic, which is to describe in more details the boundary value problem that GFEMgl Junior solves. Hello everybody, this is the second part of the GFEMgl Junior tutorial. And in this part we're going to take a look at the boundary value problem that GFEMgl Junior is set up to solve by default. So a detailed description of the problem is in the file named 2015 GFEMgl educational.pdf. So open that file. So in this section of that document we have the boundary value problem solved by GFEMgl Junior. It is a one-dimensional problem, second order boundary value problem that can represent the behavior of an elastic bar with a material property E, Young modulus E, and cross-section area A. And the problem is subject to a Dirichlet boundary condition at the left. The bar is fixed, and a Neumann boundary condition on the right-hand side at x equals L. There is a force P applied. And we are going to adopt P equals 1 in the simulations that we are going to perform next. And a key point of this problem is that the Young modulus is an oscillatory function in some part of the domain and is a smooth function elsewhere in the domain. The precise definition is given here in this equation. So between x equals 0 and 3L over 8, where L is the dimension of the global domain, the Young modulus is a constant, E sub h, and the same thing between x equals x between 5L over 8 and L. At the center part of the bar, the Young modulus follows this E tilde function, which will be given later. E sub h is, we call the homogenized property, which is given by this expression here. And for the E tilde, the values for the Young modulus are either E1 or E2. So this simulates a two-phase material with Young modulus E1 and E2. So this is illustrated in this figure, where I have the bar fixed at the left end and subjected to an axial force P at the right end. The blue part has a Young modulus E sub h, homogeneous constant material property, and at the center we have this two-phase material with Young modulus E1 and E2. And key point here is that the length of each phase is equal to delta L, which is given by L over 128. So our goal is to solve this problem using the GFEMgl and look at some variants of the method, for example, the SGFEMgl, and also look at the effect of polynomial enrichments and so on. And if you were to solve this problem with the finite element method, you can actually get exact solution as long as the finite element mesh in this region is of length L over 128. So our goal will be to use a global mesh that is much coarser than that in the global problem, and instead resolve these features of the material in the local problem only. We also have here the exact solution of this problem, so we can compute errors of the GFEMgl solution. So that's it for the description of the problem. Make sure to read the details in this document. And hello, this is the third part of our tutorial on GFEMgl Junior, and in this part we are going to take a look at some examples. And we are going to use as a guide this Excel file named Julia results with CID nodes. So this Excel file has several tabs, each one for a different set of runs, exercising one of the variations of the method. For example, this tab here uses the GFEMgl method without polynomial enrichment. The next one will be GFEMgl, where linear polynomials are used as enrichment functions. The other one, SGFEMgl, uses the SGFEM concept to modify the enrichment functions, and so on. So there are many tabs with different discretizations, I would say, or variations of the method, and they are also related to the tasks that are described in the previous document that we went over. So the solution to those tasks are contained in these tabs. So let's take a look at the tab GFEMgl. And here we have a result for several discretizations with different element size in the global problem. The global mesh element size is denoted by capital H, and the problem was solved using capital H equals L over 8, L over 16, and so on. And here we have the corresponding number of global degrees of freedom, 12 DOFs for L over 8 mesh, and so on. Here we have the energy, the strain energy computed for the case in which the local mesh, here we have the local mesh size H. For the case in which the local mesh is equal to L over 64, this is the strain energy of the enriched global problem, and this is the error in the energy norm. So in this case, it's a quite large error, as you can see. We also have the scaled condition number of the enriched global problem for at least some of the discretizations. So here I have now result for the case in which the local mesh is of size, element with size L over 128, which corresponds to the size of the microstructure, the two material phase that we saw in the previous part of this demo. We saw that the material phase is of length L over 128. And finally, this third set of data is for local mesh with element size L over 256. On this lower left part of the screen, we have the input files required to solve the problem using the GFEMgl. As we saw earlier, we need 3 files. One defining the global problem, another one for the local, and a third one for the enriched global. Here we have the files that we need to solve each one of these discretizations. So let's choose one of these and run using the Matlab code GFEMgl Junior and compare the results with the one given here. So for this demo, I will choose a global mesh corresponding to this cell here. So this cell contains the strain energy of the enriched global when we solve the global problem using element size L over 8 and local mesh size L over 128. So we need to choose the files for the 3 problems that we are going to solve in this method. So let's go back to the Matlab window. And now let's move to the folder where we have the input files. Let me move this a little bit to the right. So the folder that we are looking for is the folder named tests. Remember the GFEMgl Junior folder has a subfolder called tests. So I'll double click on that one. Then I'll move to the 598 final project 2015. Then I'll click on the GFEMgl folder. Okay, so here I have several input files for the initial global with element size 8, for example. Local problem, files for the local problem start with L, capital L. And files for the enriched global problem, they have the E sub G in their name. Okay, so to run GFEMgl Junior, we just type GFEMgl Junior on the prompt, and you ask you the file name for the initial global problem. So if I click enter, this window will pop up and show me the folder that we are just looking at earlier. And I want to solve the problem in which the global element size is L over 8. So the file name should be hvars underscore 8 L element dot dat. So here I have the file that we are looking for, H version, 8 elements in the global problem. So I select that and click open. Now the code asks me for the local problem file. So I again hit return. The window with the file browser opens again. The file name for the local problem follow this pattern. Capital L, local element size, we want 128, local capital H, and we are using 8 elements in the global problem. So here I want L for the local with 128 case, and the global mesh is the one with H over 8. Okay. So I click open, and finally the code asks for the global problem input data file. I click return. Now the pattern for the file name is one in which I have the number of elements in the global problem, in our case is 8, and EG on the file name. So I have H version, 8 elements, okay, that's the one. H version, 8 elements in the global problem, and this is for the enriched global problem. Okay, so click open. So now the code starts solving. It's computed the strain energy, and now it's finished. So before we look at the plots, let's look here at the value of the strain energy that was computed. This is the strain energy for the enriched global problem. And it says that this is the value, so let's compare with the reference value in the Excel file. And we can see that this value is matches exactly the one that we got. So everything seems to be correct. So now let's look at the results. So I have here figure 3. Where are these other ones? Okay, they are hidden here. Figure 2. I'll move them here to the bottom. If I minimize this window and this window, wait, yeah, I have the figure 1. Okay. So figure 1 represents the solution, in this case axial displacement, for the initial global problem. Let me put here the figure with the problem that you are solving again, that will help us interpret these results. So we solved the initial global problem using a mesh with element size L over 8. So essentially this will be one element, another element, and so on. And so in this region we have just two elements in this region here. And as such a mesh cannot capture the exact solution in this region well. It will be like a homogenized solution with a constant Young modulus. And that's the solution for that selection of the global mesh. On the second window, figure 2, we have the solution for the local problem, which is defined in this region. I believe that goes from L over 4 all the way to 3L over 4. And for the local mesh, we use element size L over 128, which is fine enough to resolve these features of the material in the problem, and we can indeed see the oscillations in the solution, which is caused by the change in material properties. So now we're going to use this local solution, the code uses this local solution to enrich the global solution and solve for the enriched global problem. And the solution is given here in the third window. And we can see that the enriched global solution captures the oscillations of the problem pretty well in this region, but it has a strange behavior in this region. And this happens to be the so-called blending elements. We enrich the global problem with this local solution, and so for the blending element, that would be, for example, a blending element to the right of the microstructure, that is this element here, it will have one node at 5L over 8 that is enriched with the local solution, but this second node of the element will not be enriched, and so we call that a blending element, and that is known to lead to large discretization errors. And indeed we see this strange behavior at the blending elements, so larger error than actually inside where I have the elements with all nodes enriched with the local solution. So let's go back to the Excel file. Okay, I pointed out the issue with the blending elements. And another important point is that since the local mesh is fine enough to capture the material microstructure, the error in the local problem should be 0, except that the boundary conditions that were applied are not exact. And also we can see that the local solution looks more accurate than the enriched global, again because of the blending elements. So in the next two examples that we are going to run, we are going to look at strategies to address this error in the blending elements. So for now I'll stop here, and you can try by yourself to reproduce the results that we just shown, and try to get the same strain energy as given in the Excel file.